it's gone. About what is going on with this opener. So what is actually occurring for temperature to either increase or decrease? What is the process? What is actually going on? Don't just tell me the sun, because that I know most of it comes from it, but what is actually occurring in order for us to have an increase or a decrease in temperature? What are we looking for? Well, what causes a different, why? What? Yes, the speed. Oh, you're back. Oh, did you? Oh, those tests are not. Ugh. Yeah, it has to do with kinetic energy. Okay, so the faster the objects are moving, like atoms, the more energy they have, the faster they're moving, the more in contact they're coming with each other. Did you get what we know? Okay. And then, and so we have more in contact, we have more friction, and when you have more friction, you have more heat. And then if there's less energy and there's less contact, then you have less heat. It has to do with how fast the particles are moving, or actually vibrating is the right phrase right there. Yeah, I was doing a lot of bouncing back with people last weekend, and then them shutting down the grade book and then extending the grade thing is just, I'm glad they put it in extension, but it's been a little chaotic all weekend long. All right, so the transfer of energy for our atmosphere, specifically the part that we walk around on, the troposphere, part that has weather, almost all of its energy is supplied by our sun. So the sun does its bomb thing way in the middle of our solar system, 93 million miles away from us. Now, its radiant energy can travel through space. It enters our atmosphere, it enters the troposphere, thermosphere. That thermosphere blocks that gamma radiation and those X-rays, and it heats up super hot. Even though there's like almost no matter there, it still heats up super hot. It enters the mesosphere, it enters the stratosphere. The stratosphere absorbs the UVC, 95% of the B's, and almost none of the A's. That's the part that gives you sunburn, by the way, the UVA's. Heats up. Then it enters our troposphere, and because of the fact that because it comes in contact with particles, you have, as it reaches towards the surface, you have an increase in temperature, because that's where the air is thicker. We have a more dense substance, which is good for us, so we wouldn't be able to breathe. Some of the energy, when it comes into our outer atmosphere, it scatters in different ways. Most of it just refracts, and we may talk about snow as well maybe this year, why the sky looks blue and it's not really blue, it's clear. But some of it reflects back into space, it bounces back off. So it bounces off of clouds. Anything that looks white is going to bounce the sunlight back into space. Snow. I don't know if any of you have been skiing before. There is a difference in the temperature outside if the snow is or is not on the ground. Which feels warmer if it's the same temperature? Snow or no snow, which feels warmer? No, snow does, because the light is bouncing off of the snow and it's hitting in your face. You can get a really wicked sunburn with windburn if you go skiing if you're not paying attention. Have you ever had both at the same time and you get all this, oh, it's horrible. You get all these tiny little blisters and you get an intense sunburn. Not because it's necessarily like you're walking around, it's because you're getting it from the sun itself, and then you're getting it doubly off the snow, and you get sunburned real bad on the underside of your neck. I've been to Colorado a couple times for skiing. I am having the biggest brain fart ever. Winter Park. Winter Park is where we went, and then we've also been to. It wasn't Aspen. It was one of the other parks around there. Colorado is beautiful. Mm-hmm. So we do have, this is the answer to the focus, it's controlled by how much kinetic energy is there. So I'm going back to like 8th grade science, I know I am. Potential is not moving, it is stored. The more potential, the colder it's going to be because it's not moving. Kinetic is motion energy, and the faster it's going, the quicker they're coming in contact with each other. Like I said, the more friction, that friction is what causes heat. You stop having as much friction, still possesses energy, it's just not as much, and it's going to cool off. We talked about absolute zero, I don't know if it was last week or if it was the week before, which is supposed to be the coldest temperature. So cold that there is absolutely no motion, which means electrons are no longer spinning around the nuclei, and there's zero heat whatsoever. It is a hypothetical temperature. We have never measured it. The coldest that we have is 4K, because even when you're interstellar, you still have ambient radio waves. And even though there's hardly, we say it's empty space, there's still the errant hydrogen atom here and there, but it's nowhere near enough to cause a decent measurement of heat. But the electromagnetic waves still go out into the depths of space. We have been sending out radio broadcasts every which way now since what? The 40s? When did we start radio? 30s? 40s? I mean, we've just been blasting it out 360 degrees for that amount of time. So it's going at the speed of light. So let's just say the 40s. So 40, 50, 60, 70, 80, 90,000. So we literally have a bubble 80 light years away from us in radio transmissions, which is sort of a crazy thing when you think about it. Now, they wouldn't get it until 80 years after the fact, if they got it right now. So we would still be doing whatever it was that people were doing in the 40s, way before my time. Micro, general, hero, proper, okay, to take you off this. Huey's not here. There's so many people that were sent home. I don't want to do this from home. Does anybody still need this? So I have to go back to like 8th grade because I saw it in the teats when I was double checking stuff this weekend. There are two major types of measurements. Some of them use numbers and some of them don't. The way that I taught my freshmen way back when I did IPC years ago, if it's numeric, if it has a number, it is a quantity, numerical value. It's just a letter description. It's a word without numbers. L is a qualitative. Qualitative do not have numbers in them. So if I take this desk, it's, let's see, it's smooth, it's black in color, and if I put my hands on it, it feels cold to the touch. Those are all qualitative measurements about this desk. Now, if I start giving you any kind of numerical values, such as its height, or maybe how heavy it is, which I can't default it to the ground, so I don't know how heavy it is, or if I give you the surface area of it, or if I give you the actual temperature reading from the surface, those are all numerical values, which is a quantity. It's a quantitative measurement or value. Y'all, if you spell out the word 5, F-I-V-E, it is still a number. That's always the way that I took my freshman way back then, like 14 years ago. They're like, oh, it's a word. I said, yeah, but it's a number word. It's still a number. Most of the stuff that we've done in here, especially with the station models, have been quantitative, like the temperature and the dew point and the visibility and the pressure. And if there was a precipitation amount, that was the lower right. If there was a pressure trend up or down, that was a number. Those are all quantitative. Now, there was one qualitative one that we had, which actually had both. We did wind. Now, the direction of the wind was qualitative. It was an easterly wind, or it was a northwesterly wind. But the speed at which it traveled in knots, 25 knots, 10 knots, 5 knots, that's a quantitative value. So the wind actually has both. You could compare the temperature and the dew point and find your relative humidity, but it's still a percentage. It's still a number. you really should have heard these phrases, and you should have heard them in chemistry too. I know we covered it in my chemistry class. We did precision and accuracy at the same time. So once again, numbers is a quantity. Non-numerical or just a word, a letter description, a word description is a qualitative measurement. But you really should have seen, this is probably the third time that you've seen this. At least the second time you've seen it was a minute to do it with chemistry. So all heat is the transfer of energy between objects that are at different temperatures. Now they're going to keep exchanging heat energy until they're the same temperature. Then it stops. But until it stops, until it's in equilibrium, same temperature, it always goes from a higher temperature, which is more energy, to the lower temperature, which is less energy. As that's the way everything works in nature. It goes from high concentration to low concentration. Now, we're not going to get into like active transport and biology and cells and sodium, potassium, no, thank you. Things go from high concentration to low concentration. So if I have a balloon of helium and I pop it, it's not going to stay a bubble of helium. It's going to spread out because it was this concentrated pocket. And then when I pop it, you can't see the helium gas, but it does spread out evenly throughout the room. This is the second law of thermodynamics, and people always get it wrong. Let me give you the example that you're going to get wrong. If you have a glass of water just from the sink, just tap water, and you put ice into that glass of water, which way does the heat go? From where to where? Okay, it goes from the water to the ice. Everybody says, oh, look, because the ice makes the water cold, so it goes from the ice cube to the water. No, it goes from the warmer, which is tap water should be about room temperature, give or take. It goes from the water into the ice cube. My first period goes, so the ice cube is like a heat sponge. And I was like, yeah, it's not a water sponge. Yeah, it's a heat sponge. And then when the ice absorbs that heat, it starts to melt.
That's why it melts, isn't it?
That is exactly true. That is why it melts. So if I put my hand on the desk and it feels cold, which way is the heat going? Going from my hands into the desk because it feels cold to me. So my tabletop is literally a heat sponge. It is taking the energy from me. Okay, if your parents were like mine and they're like, go ahead and let them hurt themselves because that's how the kids learn. We used to have the old school burners on the oven, like the coils, not a flat top. And it's obviously when it's hot, it's red, right? Okay, so here I am 6 years old and it's no longer red. So guess what I did? I touched it. And for a fraction of a second, I did nothing. And then I screamed, bloody murder, because I had, thankfully it did not like, what's it called when people get the tattoos but they burn them? It's on a brand. I didn't actually brand my hand. I pulled that fast enough. Did I ever touch the surface of the oven again? No. I learned really quick that was painful, and I didn't do it again. So for the brief second when I touched that burner, which way was the energy going? From the burner to my hand very quickly, which is what actually causes a burn. Y'all, the same thing happens with dry ice, which is very cold. If you're dumb enough to pick it up, it's going to burn you. It burns you with cold. It's that rapid transfer of heat from, in this case, your hand to it that actually burns your skin. It doesn't have to be hot to burn you. It's a rapid transfer of heat from one object to another that burns our sensitive flesh. It does not take much to hurt us. We're extremely fragile. Okay, so once you have an equilibrium, which means there's the same amount of heat energy in both objects, the heat stops transferring. Okay, my allergies are still bad enough. No, I can't wait until the virus is gone. I do not need to wear this thing anymore. I'm not working. This pollen is sort of hoping that that cold front would have knocked it all out, but you just brought something else in. should be ready. So we have transfer 1 of 3 ways. These words also should not be new to you. You just need to have a refresher. We're going to go over them just real quickly. I need to check my one thing. And then we'll talk about each one individually more in depth. Conduction is the touching between objects, almost always solids. Doesn't have to be a solid, but it's the best through solids. Like when you touch a hot burner and for a brief second before you say bad words and you pull away, you have a quick transfer of energy. Currents, air conditioning works this way. And just because you guys remember gross stuff better than anything else, if you go to a water park, they have a lazy river. You ever notice sometimes you go through a warm spot? Mm-hmm. Yeah, you know what that warm spot is, right? Mm-hmm. It's pee. All right, but it only stays a pocket of warm until it spreads out, and it just evenly tries to heat the lazy river. I hate public pools. People pee in the pool, it's gross. So conduction is something that can flow, or conduction is normally a solid. It's vibrational energy transfer. And we'll come back and do them in depth in a second. Convection is something that can flow. It's a current. Yes, it can be a gas and it can be a liquid. Radiation almost always talks about the sun. Doesn't have to be the sun. Normally the sun's involved in some way, shape, or form. Radiation is the only one that does not need matter to go through space. We'll do it in depth in a second. Now water, it's sort of out of place, but you need to know this, and we may go in depth when we talk about ocean currents, and when we go into depth next 6 weeks. No, that's the 4th 6 weeks. Water is really the secret to life on this planet. If water didn't have the properties it has, life would not be the way it is. Water has so many unique properties. One of them being an extremely high specific heat, which means it takes a lot of energy to heat it up, and it takes a lot, so it takes a while for it to heat up, but it also takes a lot of energy and time in order for it to cool back off, which is why if you live on the coast, the difference in temperature between your day and your night really isn't that great because it's humid. The moisture in the air holds on to the heat, but if you've ever visited the desert, the temperature difference between the day and the night can be 80 degrees different sometimes because there's less moisture in the air. And therefore, it can't hold on to the heat as much, and you have a wild temperature swing. That's why that happens. That's also why, if you're making spaghetti, it seems like when you watch water, it takes longer to boil. It seems like it takes forever for that water to heat up. But that same pan without water in it, you turn it on, you stick your hand in the pan, and you burn snot out of yourself. Because metal has a much lower specific heat. Therefore, it heats up and cools off much faster. They are good conductors of heat. Water is not a good conductor of heat because it has a high specific heat. In fact, of all of the natural materials on this planet, it has the highest specific heat. And it gets the value of 1 because we say so. We assigned numbers to all of these concepts. 1 is a very common number that we like to use. Also, not that I've ever known anybody to do this, but I do remember when I was a child, because we had very, very long periods of cold. And when I say cold, like -0, like below 0 kind of cold, where you'd have long periods of time where the power would be out. And yes, we had a kerosene heater. We didn't have a fireplace, but a kerosene heater. But what we were told to do, and I don't ever remember my parents doing this, is any sink or any tub, they recommended that you fill to the brim with water because that actually helps keep your house warmer. That water will absorb the heat and it will slowly give it off into the air that's directly above it in evaporation. I've never known anybody to do it, but I do remember being told to do that when I was a kid. Well, not me, my parents. My parents just never did it. Conduction, first, touch. This is going to be seen the best. Doesn't have to be it, but the best through solids. It can happen between a liquid and a gas. So the surface of the ocean, we just talked about storms. When it's really, really, really warm, it goes from the liquid into the gas that is directly touching it. Now that then gets lifted through convection as it rises and it gets spun into a spiral from the Coriolis effect, and then it makes land and it dissipates. But conduction happens the best between solid objects. Okay, well, we talked about with the water in the ice cube, where the water is literally touching the ice cube is considered conduction. Then that water, which is cooled off, starts circulating within the liquid. That is convection. But the actual direct contact with the ice cube, which is a solid, is touch, which is conduction. Your warmer molecules are going to be vibrating faster than the colder ones. That vibration gets passed off to the ones that are not as quick. They start becoming equilibrium, and then those spread out to do wherever it's moving it through the rest of the object. Whatever that object is that you're trying to heat. Do what? I believe that's on the next slide. At least I think it's on the next slide. No, it's on this one. Okay, so in our atmosphere, it's going to happen where it is the most dense, which is going to be closer to sea level. Like I said, specifically between the surface of the land and the surface of the ocean, and with the air that is directly above it. Because as soon as you get the next molecule away, that transfer is now convection. It's no longer conduction. Now, your oceans hold on to the energy of the sun much better than land does. Water has a higher specific heat than land does. But you do still have transfer of energy from the surface, wherever that surface is, with the air above it. Now, keep in mind, I will not be here tomorrow. I might be here first thing in the morning if I could finish setting up for a sub. But I do have an assignment that's being left behind. That computer apparently does not actually have Adobe loaded on it. And every time I try to create a PDF, it keeps telling me to buy it. And I'm not going to buy it. It should be on my school computer. So instead of being able to upload a PDF of the assignment where it's easier to like draw on it, it's a Google Doc. You guys should all have Cami downloaded as an extension. So you can either use Cami, because it's a word search. And I don't want to leave anything paper behind for the substitute. Everything should be digital, so make sure you've got your Chromebook. I'll make sure that whatever those things are called are spread around the room. Thank you. The things that you can plug into your electricity, those. So you can either use Cami, or, I mean, if you really want to take the time, you can highlight the letters and change the font color. That would take you forever. So if you don't have Cami, you need to download Cami, because I can't get it. And I even tried it from home, and when I export it as a PDF through a website, it's not giving me the option to force you to make a copy, which means everybody is editing the same document. So that won't work. I need to get with Mr. Connor and figure out why I do not have access to proper PDFs on my computer, because I should. Right, convection, things that can flow. Liquids and gases, technically plasma too. We just don't, we're not walking on the surface of the sun. Technically, plasma has a convection current too. We're sort of ignoring that state of matter. We talk about it a whole bunch in the first 6 weeks, and then we just sort of ignore it. As you heat a fluid, it is going to become less dense. There is one exception, that is water that is below 4 degrees Celsius. I'm going to ignore that for right now. But in general, as a fluid heats up, it expands, it becomes less dense, and it rises. And then once it rises, especially in our atmosphere, lower pressure starts cooling off, it condenses, and it sinks. When you heat water, like for spaghetti, it's going to obviously heat on the bottom of the pan. The sides of your pan are warmer, so the heat will go along the edges up to the top where it starts to cool off, and then it will sink in the middle. This is actually exactly what happens in a hurricane. So you've got your heat from the surface of the ocean. It's the stool. Hello? Okay. Okay. Oh, okay, awesome. Awesome, thank you. Good. Thank you. Okay, bye-bye. Okay, I'm so sorry. That was a 444, so I thought it was like my kid, like, is sick. Like, that's always my fear. If it's a 444, like, ah! This is cool now. There's my doctor. I'm good. It's like, until y'all get older. It's not fun. Okay, so as I was saying before my phone died, so the heat on the bottom of the pan is going to be warmer on the outside, just like a hurricane. So you've got heat from the ocean, and on the outside is warmer. As it cools, it then has that downdraft of cold air right in the center, which causes the eye. And the next time you boil spaghetti, which I don't know if you make your own spaghetti or not, if you look, you can sort of see. I mean, it's not like an eye wall like a hurricane, but you can see how it's all going down in the center because that's where it's cooler. It's the exact same concept as a hurricane. The exact same concept. Does anybody still need this one? No? Okay. Air is constantly having an exchange of hot and cold. And we see this the most with Coriolis effect. The more dramatic the temperature change between air masses, the stronger. Okay, I thought maybe that was like, that is a proper sentence. I thought maybe I left the word off. So the bigger the difference between the warm and the cold front, between the high and the low pressure, the more dramatic your storms are going to be, because you have the bigger temperature change, bigger pressure difference, stronger winds. The stronger winds are going to whip these storms for us. Here, it's a tornado. It can whip them into that counterclockwise flow, which is also pulled towards the center in this case. Then it creates that funnel cloud. It's the same thing as a hurricane. You guys just aren't used to hurricanes. I am, which is why I talk about them more, because I've dealt with them for so much time. But you've got that counterclockwise, low pressure, counterclockwise in, which is what makes it have a circular, or in the case of a tornado, funnel. It's the same thing. Holds it together, spinning counterclockwise. You still have a downdraft of cold in the center, and you have an updraft of warm along the outside. High pressures spin clockwise, and they push out. Low pressures spin counterclockwise, and they pull in. Now, granted, that is for the northern hemisphere. If you move to the southern hemisphere, same concept, but reverse the directions. And we mentioned this before, it was 80 degrees Fahrenheit. That's what it has to be more prone for hurricane development. The higher the temperature, in general, this is not 100% because there are other factors besides temperature, the stronger that storm is going to be. And I didn't check the Gulf last weekend, but the weekend before it was still 84 degrees, which is insane. And I don't think there was an area of interest when I was looking at this last week, but I had a feeling it's disappeared. I did cheat and look at my app. I said, y'all haven't had to. Y'all deal with the little brother that's more energetic and causes, oh no, there is still stuff out there. Hurricane season does not end until the end of February. It is called Epsilon. It is out there. Looks like it's not going to be a threat to us though. Gonna hook up the East Coast. But yeah, we deal with the little brother tornado, which has a lot of energy. Hurricanes actually have more energy. They're lower pressure, but they have more time to rain it out. A tornado, it still has a lot of energy, but it exerts it in such a short period of time. They're more destructive, which is why they become windier. An EF5 can be over 200 miles an hour. Where a Category 5 hurricane, they start at 157, if I'm remembering right. Still don't want to be in contact with a hurricane or a tornado at all, but your tornadoes, their winds are way worse because they're taking all that energy and they're over a short period of time. Most tornadoes don't last more than a few minutes. Your little ones don't last hardly any time at all. Your big ones can go for a few miles before they finally dissipate.
And the really bad tornadoes last hours.
Well, let me see how long. What was the name of the town? I want to say it was in Alabama. The town started with a J. And this was back in 2012-ish, and it just devastated the, here, worst category, no, EF5 tornadoes. As soon as I see it, I'll remember it. Nothing more. List of F5 and EF5 tornadoes. With a J, I can't remember the name of the town. I was looking for an actual chart. It lied to me. Go figure, the internet did not tell me the truth. Convection currents drive what is called the Coriolis effect, which is this image. And no, we're not going to do the Coriolis effect in depth now. That's supposed to be in the 4-6 weeks, and we'll talk about Hadley cells and trade winds and the easterlies and the westerlies. I can tell you that the trade winds were called the trade winds because back in the day, before we had airplanes, our main travel was through boat for shipping. You can think of like the old pirate ships. I think they were called frigates. The ones with the really big sails, like multiple big sails. They got to Europe from us on these trade winds. That's what actually pulled them. They had to go in a certain area. They couldn't go to New York. But they actually push you back the other way up there. But below 30 degrees latitude, which when I was talking about hurricanes, that's where those hurricanes hook east, is when they cross that 30-degree latitude, and most of them are going into poor Louisiana. But that's where they switch from going this direction back the other way. But that they're called trade winds because that's what we used for trade. So you would take the lower route underneath 30 to go from Europe over to like the Caribbean, more towards Mexico. But then in order to go back, they would use the westerly winds in order to get back. They would be fighting against the wind. Now with sails, you can cheat. The way you do the rigging is if you set it up right, the wind that's coming towards you actually will make you go into it. It's called vectors. If you guys take physics, you should learn. You should learn about vectors. Tri-state tornado. Oh, these are all from like the 1800s. I'm not going to find it. The internet's failing me today. But the Coriolis effect towards the equator are the tropics. Okay, those are your warm ones that have the most energy. Your tropic maritime are going to also have the most moisture. But they're, like if you notice, they're going the same direction, but you're going south and north, depending on if you're north or south pole, which is why the stuff spins the opposite direction. But they're going towards the equator where it's the warmest. And so this Coriolis effect is spinning, in this case, is clockwise. Your westerlies then, same thing, but they're going towards, and this would be your polar masses. Those are now spinning counterclockwise. Then you have your Arctic masses, which switch direction yet again. And your coldest of your air, because I just made your test last weekend for Thursday. The coldest of your wind are your Arctic blasts. Then comes your polar ones, which are the next section in, so the northern part of the United States. And then your warmest will end up being your tropics, which would be down towards Mexico and down to all the Venezuela, Guatemala, all the South American, what do you call it, Panama. The bridge between North and South America. What are those groups of countries called? Latin America? Is it Latin America? Between North and all these countries, between Mexico and South America, there's a term for it. I want to say it's Latin America. Central America? Okay, thank you. That was not my strong point. There's not at all. Like, no. History and that kind of stuff, no. Okay, advection is a specific type of convection that deals with both the air, the atmosphere, and the ocean. But this is this horizontal band that's within the tropics. So this particular section is specifically advection. It is the horizontal transfer of heat through fluids. So the atmosphere, the gas, and the liquid, the fluid, the water part, as you go through the equator. What's it called? GMT, is it? That's gonna bother me. I remember the name of that EF5. There was a really big one in the early 2000s that went straight through Oklahoma City that I remember. It's, I don't want to go through tornado. I don't want to go through any major thing like that ever again. Okay, convection. So convection currents also happen underneath our feet, a couple miles down, and we have the mantle. That's what drives plate tectonics. We will do plate tectonics next 6 weeks. You don't need to know what a slab pull is and a ridge. We'll get into all of that as we do this later on this year, this semester. But you've got your outer core. You can't see me pointing online. Your outer core, which is molten iron, which is extremely hot. So you have a lifting of that temperature, because even though it's molten iron, and then you've got magma, which is a mixture of different elements that are in here. It's not all iron, but you have a lifting. This ridge is what happens when the plates get pulled apart, and then the mantle comes up, and this happens more at like the depths of the ocean, okay, than anywhere else. But you have this cracking apart between the plates when they separate, and then the asthenosphere is what allows these to cool off and then sink back down, and then they're eventually going to heat back up and rise. Exact same thing as boiling spaghetti, but it's not water and spaghetti, it's molten iron and silica and other elements that are deep within the earth. Now you have, when we do tectonics, your major, not earthquakes, okay, your actual plate motion. Your most common thing is going to be to split, and then you have your magma come up, or you're going to have one sliding over the other. And deep in the ocean, when it does do that, it does it in a jerk. That's what causes tsunamis. It's like an earthquake, as these things slide past each other, but it's not a smooth slide. It's pressure builds up, and then all of a sudden you have a jerk of motion, and sometimes you have a collapse. And if it's close enough to shore, then you have a massive tidal wave coming in. And that happens Christmas Day in Indonesia. Can't remember the year, but it killed a whole bunch of people. There were a bunch of tourists. They were just watching. Y'all, if you go to the beach, and all of a sudden it looks like the ocean gets sucked into itself, run. That is your last, and opposite, you're going to see birds, and the animals are going to break out of their pens, and they're going to go up in elevation because they know. When the ocean looks like it is not low tide, like it's literally coming and it's sucking itself up, it is building up to make a tsunami wave. Up in elevation, run. Because once you see the water coming, it is too late. We'll get into all that kind of stuff. And unfortunately, there is footage. There's a lot of footage of that. I try to find ones where you don't see bodies floating around, but unfortunately, that happened. Radiation normally involves the sun. Anything that exists can give off radiant energy. It does not need matter, and it can travel through space. This should be the last slide. Look at this. Yes, it is. Here's kind of it. Anything that exists gives off a heat signature. We see that as infrared. You've ever seen the movie The Predator? Okay, the way the predator sees, like in reds that are hot and whites that are even hotter and the blues and greens that are colder, that's radiant energy. We have goggles that we can put on and see it. You can't run from the cops at night because they either have that or they have night vision, that they can see you. You cannot hide at night. They will find you. Huh? So, what comes through our atmosphere Okay, so the thermosphere blocks the X-rays and the gamma, why it's so hot. The stratosphere blocks most of the UV, well, all the UVC, most of the UVB, none of the UVA. But that's why it's hot. So what comes through is some of that UV, okay, but all of the light energy, all of the infrared, all of the going down microwaves and then radio waves. Those come through our atmosphere, no problem. And that's what actually causes the heating of the lower atmosphere. It's that particular part, specifically the infrared. And I'm going to freeze this, because I know that there's stuff on here. Okay, hold on. Check online, check attendance. Okay, so now did you already redo that test better, or you haven't done it yet? You have not redone it yet. Okay, so as I haven't seen who's online, so once again, the station models, you need to, if you really don't get it done, I would say by 3:30. I'm probably going to miss it because they're pulling grades at 4, and we can't touch the grade book until Friday. So this is the one from Friday. Sheila, Blake, Tyler, Corbin, Jace, Guy, Parker, Isabel, Ty, Gunnar, and Emily. Those are the ones I did not see as of this morning. Now, if you did it since I checked at 6 o'clock, 6:30 this morning, I just haven't seen it. You guys do have a few minutes if you need to do today's. What you got? Did you just take it?
No, I had it done the class period.
Or hold on. Different Josh. Different Josh, I bet
She
you.
said Ty.
Yeah, I did. Other Josh. I just read the word Josh. You mean Josh, and I thought it was you. No, I have yours. I apologize. The other Josh. I have so many. You see, in my 7th period class, I have 2 Ryans. I have 3 Madisons. I have somebody else. So some other, like, it's, I'm going to have to, I see Amanda. I see you. Yes, Sanchez. Okay, I'm going to